So next up, we have Mark from Indiana University, Purdue University. So Mark is currently a postdoc at the Integrated Nanosystems Development Institute at Indiana University, Purdue University, focused on developing new methods to sample and identify VOCs in breath. Completed his PhD recently in the summer of 2022, where he concentrated on utilizing chemometric approaches to identify VOC biomarkers for prostate cancer, breast cancer, hypoglycemia, COVID-19, and clinical traits of cystic fibrosis. Over to you, Mark, and thank you.
Hello, all. My name is Mark Woollam, and I'm very excited to be here today virtually for the 2022 Alstone Breath Biopsy Conference, giving an early career talk. I just got my PhD in analytical chemistry from IUPUI in the summer of 2022. And now I'm a postdoctoral researcher at Integrated Nanosystems Development Institute. And today I'm going to talk to you about canine-inspired identification of exhaled volatile organic compound biomarkers of different diseases. So before I get into the meat of the presentation, I'm just going to give a little bit of background information. We all know that canines can be trained to detect different diseases with very high sensitivity and specificity because they can smell volatile organic compound biomarkers. The reason they can do this so efficiently is because they possess a very sensitive olfactory system with over 300 million receptors. Researchers have been trying to identify VOC biomarkers to harness them for non-invasive diagnostic applications. And some of the most common sample types include urine, sweat, and of course, breath. And the reason why breath is so interesting is because it's virtually limitless in nature and it's an abundant source of VOCs. There are hundreds of VOCs in breath that are produced from the human body, and they come from both endogenous and exogenous sources. VOCs are byproducts of biological processes, including metabolic pathways, and that's what we're really focused on for biomarker discovery, because metabolic pathways are uniquely dysregulated by different diseases. However, VOC biomarker discovery is very complex because of the fact that VOCs display large heterogeneity, because many different factors can affect their expression levels, and these include environmental variables, medications, and so on and so forth. So what are the materials and methods that we use to profile VOCs in breath? The gold standard for breath analysis is using adsorption tubes, but these require a thermal desorption unit, which can be expensive. So an alternative is using solid phase microextraction or SPEME. And what we do is we collect VOCs in a Tedlar bag through a viral filter, and we cryothermally transfer them to a headspace vial at very low temperatures using a flow-regulated vacuum. We can store the vials at -80°C and then perform SPEME coupled to gas chromatography mass spectrometry, or GCMS, for quantitative profiling. We've actually compared this cryothermal transfer method to a method we call Tedlar SPEME, which is just exposing the SPEME fiber in a Tedlar bag. And as you can see on the heat map to the right, the cryotransfer method was very sensitive, more sensitive than Tedlar SPEME for the majority of VOCs and breath samples. There were a subset of VOCs that were more sensitive using the Tedlar SPEME method, and these mostly consisted of small molecules with low molecular weight. So using the cryotransfer method, I'm going to present some results on profiling VOC biomarkers related to hypoglycemia in patients with type 1 diabetes. So what we did was the team went to a diabetes youth camp called Camp John Warville in northern Indiana, and we would collect breath samples from the campers. And right before they gave a breath sample, they got their glucose measured using a glucose meter just to ensure they were euglycemic or hypoglycemic. So SPEME GCMS results showed a large number of VOCs that were dysregulated by hypoglycemic events. And we collected samples in 2 different summers. We had one summer as a discovery cohort, and the second summer served as a validation cohort. And we saw a large number of VOCs in both data sets. And as you can see in the heat maps, there were VOCs that were both upregulated and downregulated by hypoglycemia in both data sets, and they tended to display high interclass variation and low intra-class variation. We identified 40 conserved VOCs between both data sets, the training and the validation, And we use forward feature selection coupled to linear discriminant analysis to build a predictive classification model and identify a small biosignature of VOCs that could predict hypoglycemic events. And as you can see, a biosignature of 6 VOCs had a validated sensitivity and specificity over 90% in both sample cohorts. You can see the two-dimensional LDA plot on the left-hand side and the associated receiver operator characteristic curves on the right-hand side. So now I'm going to transition into correlating VOCs and exhaled breath to different clinical traits of cystic fibrosis. And here we really want to harness VOCs to potentially use them to monitor patient adherence to treatment and also characterize baseline pulmonary function. So before we looked at the VOCs, we assessed the quantitative clinical traits and we compared them between the categorical variables. And we really saw no major differences in the quantitative variables. However, we did see that forced expiratory volume was significantly decreased in patients undergoing pulmonary exacerbations, which are pretty much just coughing fits. And this is expected because forced expiratory volume in 1 second is used for pulmonary exacerbation diagnosis. So first, regarding the VOC analysis, we correlated VOCs to the use of Trikafta, which is a highly effective modulator therapy. And very interestingly, we saw 2 volatile aldehydes, octanol and nonanol, were significantly upregulated in patients not taking the treatment. And this is very interesting because volatile aldehydes in general have been correlated to increases in oxidative stress and lipid metabolism. So potentially one day, we need to validate these results, but aldehydes could monitor if the cystic fibrosis patients are taking this therapy. Lastly, we correlated VOC output to pulmonary exacerbations and forced expiratory volume in 1 second. And as you can see, a saturated hydrocarbon 3,7-dimethyldecaine displayed significant correlations with forced expiratory volume in 1 second. And furthermore, this VOC was significantly downregulated in pulmonary exacerbations. This was sample cohort with limited number of samples. That is a downfall. So we couldn't really use our multivariate chemometric approaches here because we would just produce overfit models. But that's something that we may be able to explore in the future. And lastly, I'm going to be switching gears here. This is a project that I hold very close to my heart. And it's developing in-house solid phase microextraction fibers for VOC detection. So all of the results that I previously went over used GCMS, and mass spec in general is a great approach for profiling VOCs, but it's not very portable in most cases. And it would be much more ideal to have a miniaturized nanosensor to detect diseases at a point of care. However, current sensors are not very selective. They are very sensitive, but not selective to different VOC biomarkers. So an idea that our lab had was, can we coat gas sensing layers on SPME fibers, expose them to a complex matrix like urine or breath, and use GCMS to understand how multiple VOCs are interacting with that gas sensing layer quickly. Because when you do this using sensors, when you're qualifying sensitivity and selectivity, you have to run individual VOCs one at a time because there's no mode of chromatographic separation or even VOC identification. So we have shown that polyvinylidene fluoride carbon black composites can be coated on SPME fibers. And as you increase the amount of carbon black, you increase VOC sensitivity. You can see this in the upper right-hand corner using SPME fibers and detecting 2,4-dimethylbenzaldehyde. And we really saw an increase in sensitivity for all of the VOCs in urine, so it wasn't really selective towards one analyte. But we did explore the reason why this was occurring, and we saw that as you increase the amount of carbon black in the composite, the hydrophobicity increases, as you can see through the contact angle characterization. So we do need to develop more selective sensing layers, but we have shown that SPME GCMS is an efficient tool to characterize sensing layers very quickly. And lastly, some of the work that we're currently working on is electrospinning SPME fibers. I want to give a special shout out to my colleague, P.S. Biswas, who does all the electrospinning. I can't take credit for that one. And you can see some SEM images of electrospun SPME fibers on the lower right-hand side. And preliminarily, just by electrospinning the same materials, PVDF carbon black, we can enhance the extraction efficiency by a factor of 3. So that's pretty cool. So in conclusion, VOCs in exhaled breath were shown to be biomarkers for hypoglycemia in a large sample cohort. Preliminary studies for patients with cystic fibrosis show that breath analysis may be a really efficient strategy to monitor treatment adherence and baseline pulmonary function, although we did have limited number of samples. And then finally, SPME fiber fabrication and GCMS analysis is an easy and quick way to assess sensing layer ability to absorb VOCs that are present in a complex mixture, such as urine and or breath. So some of the future work that we're striving towards is we want to develop an integrated nanosensor system to detect VOCs that were related to hypoglycemia that we identified in the GCMS studies. And we want to validate the preliminary VOC results for monitoring the clinical traits of cystic fibrosis. We also want to identify VOC heterogeneity and establish healthy baselines in large sample cohorts. That's actually an ongoing study that's funded by the Defense Threat Reduction Agency. And furthermore, for the SPME fiber fabrication project, we want to explore other materials and potentially increase the selectivity of current gas sensing layers. So I would like to acknowledge all of my lab mates, Arai Scholes, Mariana Maciel, and of course, my advisor, Dr. Mangalal Agarwal. And I would also like to acknowledge the IU School of Medicine, the School of Science at IUPUI, the School of Engineering and Technology, and of course, all of you for your attention today. And I hope you have a good rest of your conference.
Excellent. Thanks so much, Mark. So I can see you if you unmute your microphone. Can you hear me okay?
Yes, sir. Thank you.
Brilliant. Thanks so much for the talk. We've got a few minutes for questions. First one I had, in the hypoglycemia model, you had 6 VOCs, and when you showed the ROC curves, so in the training set, AUC was 0.98, and then in the test set, you had 0.93. Was that test set built by holding back samples, or was that tested in a prospective validation study with new samples being collected?
Yeah, there was no cross-validation or holdout. It was completely blind. The transformation matrix that was generated by LDA was just multiplied on those new samples. So it was completely blind and independent.
Wow.
If that makes sense.
Yeah. So new samples collected, you applied the model, and that was the performance that you got?
Yes, sir.
That's very good. That's very good.
Yeah, especially with the number of samples that were collected, it was definitely one of like the coolest things that I've seen in my time. So
that's great. Questions come through. Did you also consider testing for hyperglycemia? Hypoglycemia is often clinically apparent, symptomatic, but hyperglycemia is not, and can also be an indicator of different problem, a new illness caused by diabetes to worsen.
Yeah, no, that's a great question. Our team has not done that so far. We have done some previous clamp studies where we systematically lower the glucose level. And we're trying to find potential correlations with actual blood glucose, which may be able to be extended to hyper. But unfortunately, we have not, and that is definitely a great idea for future studies.
Brilliant, thanks. One's come through. Acetone's a known biomarker in breath for hypoglycemia. What's the goal or purpose of identifying alternative or additional VOCs?
No, that's a great question. Acetone is definitely a biomarker for hypoglycemia. And just looking at literature, acetone has also been indicated as a biomarker for many different diseases. Yeah. So it's not necessarily disease specific. Unfortunately, this biosignature that we came up with, we did not directly test for disease specificity, but I think a biosignature in general is going to be more likely to be disease specific than a single VOC. But I'm not trying to discount acetone. Acetone is important, but there may be other analytes.
Brilliant. There's a question related to the SPME fiber coding. So that's a really interesting idea, coding. It sounds like the main goal is to get enhanced specificity there. is that the case? I was wondering if you could elaborate a little bit further on the types of selection criteria you would use to, pick those coatings to apply to the speaking fiber.
Yeah, no, that's definitely a great question. I think that's one of the hardest things to increase the selectivity. But so thus far, we really don't have a very selective coating. I think we saw a presentation earlier about molecular imprinted polymers. Because we always try to think about the intermolecular interactions. We're not covalently binding these VOCs, so we're thinking about the intermolecular interactions between the coating and the VOCs. So if we're going for alcohols, we could do hydrogen bonding. Of course, for breath, since it's a water factory, it may not be the best, but just for an example. But I think the best way to potentially do increasing selectivity is creating a pocket or an artificial pocket, or even biological engineering one to increase selectivity.
Fantastic. Well, thank you so much, Mark, for the wonderful talk and taking the time to answer the questions as well. Very much appreciate it, and good luck with all your future research.
Thank you, sir.